In this lesson, we're looking at working through some examples using integration by parts as a process. So we'll start with the first example. We're looking at the integral of x cos x dx. Now if we use Lipit, there's no logs, there's no inverse trig. The x represents a polynomial, so that means that we can let u equal x, and therefore dv dx will be cos x. Du dx will be 1, and therefore v, which is the integral of cos x, will be sin x. Now that we've done that, we know that our integral of x cos x dx will be equal to uv, which is x sin x, subtract the integral of v du dx, which means we've got 1 multiplied by sin x dx. Okay, so this becomes x sin x subtract the integral of sin x dx. The integral of sin x is negative cos x, so now we've got x sin x plus cos x plus c, and there we have our integral of x cos x using the process of integration by parts. Okay, so we'll move on to the second one. Now we're looking at the integral of x e to the power of x with respect to x. Okay, so in this scenario, again, e is an exponential, p is a polynomial power, so u must be x, and dv dx must be e to the x. Du dx is 1, and v is the integral of e to the x, which is e to the x. So we're looking at the integral of x e to the x with respect to x will be the product of uv, which is x e to the power of x, subtract the integral of v du dx, which will be 1 times e to the power of x with respect to x. So we've got x e to the x, subtract the integral of e to the power of x with respect to x, which will give us x e to the x, subtract e to the x plus c. And there we have it, there's our integral. Now when we look at the third one, we've got the integral of arc sine x. Okay, we know the derivative of arc sine, but we don't know the integral. So we'll start by looking at Lipit's. Now obviously there's an issue here because there's only one thing, so we're going to consider this as 1 multiplied by sine to the negative 1x dx. And so that means that this will be inverse trig, this will be polynomial or power, so u will be the inverse trig, which will be arc sine of x, and dv dx will be 1. Derivative of arc sine is 1 on square root of 1 take x squared, and v, the integral of dv dx, will be x. So now we're saying the integral of arc sine x with respect to x is equal to uv, which is x sine to the negative 1 of x, subtract the integral of v du dx, which means we've got x over the square root of 1 take x squared dx. So that means we've got x arc sine x, and we can see that this is going to be a substitution. So we'll let u equal 1 take x squared, and therefore du dx is negative 2x, which means that dx is equal to negative 1 over 2x du. And when we put this all back in, then we've got x sine to the negative 1 of x, subtract the integral of x over square root of u multiplied by negative 1 on 2x du. Our x will cancel, and we're left with x arc sine to the negative 1 of x plus 1/2 the integral of 1 on square root of u, which is u to the negative 1/2 du. And so now this will be x sine to the negative 1 of x plus 1/2 u to the power of a half over 1/2. So the halves cancel. Don't forget Charlie. That means we've got x arc sine of x plus the square root of 1 take x squared plus c. And there we have it. There's our integral of arc sine of x. Okay. So there's our first 3 examples. Obviously the last one's a little bit more challenging. The integral is harder because we're using a substitution method within this by parts. Now we're going to move on to another example. Now this example is harder because it will involve an iterative process, and you'll see that in a second. So I'm actually going to start by saying let the integral of x squared e to the power of x dot dx equal a. So that means we can let the integral equal a for the whole process. It makes it easier at the end. In this sense, we've got a polynomial and an exponential, so it makes sense that the polynomial is u, and the exponential dv dx e to the power of x. Now du dx will be 2x, and v will be e to the power of x. So when we find this integral, we've got a is equal to uv, which is x squared e to the power of x, subtract the integral of v du dx. So that means we've got 2x e to the power of x dx. Now this isn't an integral we can do, and we have to use by parts again. Alright, so what I'm going to say is that we're going to consider the integral of 2x e to the power of x dot dx. And so in this case, u is equal to 2x, dv dx is equal to e to the power of x. The derivative here, du dx, is 2, and the integral is e to the power of x. So that means the integral of 2x e to the power of x with respect to x is uv, which is 2x e to the power of x, subtract the integral of v du dx, which means we're looking at 2e to the x. Now this is an integral we can find. So this will be 2x e to the x subtract 2e to the x plus c. So now we can substitute this back into a. So sub into a. So we've got a is equal to x squared e to the power of x, subtract this integral, which is 2x e to the x, subtract 2e to the x plus c. So we have x squared e to the x, subtract 2x e to the x plus 2e to the x plus c. If we see a common factor here of e to the x, we've got inside the bracket x squared, take 2x plus 2 plus c. And so this here is our final integral. Our second last example is going to be another iterative process, but this will take a couple of iterations, and it also requires us to see the relationship between some of the subsequent integrals and the original. So we're taking the same approach at the start. We're letting a equal the integral of e to the power of x cos x dx. So here we'll let u be e to the x, and we'll let dv dx be cos x. So du dx is nice and easy, it's e to the x. V is nice and easy, it's sine x. And therefore a is equal to uv, which is sine x e to the x, subtract the integral of v du dx, which is e to the x sine x dx. Now this we cannot do without using by parts. So we have to consider the integral of e to the x sine x dx. Now u is e to the x, dv dx is equal to sine x, And from there we can say du dx is e to the x, and v is equal to negative cos x. Now that means that the integral of e to the x sine x dot dx is equivalent to uv, which is negative e to the x cos x, subtract the integral of v du dx. So v du dx is negative cos x e to the x. That'll make this positive. And we've got cos x e to the x with respect to x. Now this should be familiar. Right at the start, we let a equal e to the x cos x, or the integral of e to the x cos x. So that means this is actually equal to negative e to the x cos x plus a. So now we can sub this back in. So we can sub into original, and we've got a is equal to sine x e to the x, subtract the integral of e to the x sine x dx, which is negative e to the x cos x plus a. So we've got a is equal to sine x e to the x plus e to the x cos x, and subtract a. So 2a is equal to, if we take out a common factor of e to the x, we've got e to the x sine x plus cos x. Now I've realized I've forgotten a few charlies here. Put him back in. And therefore a is equal to 1/2 e to the x sine x plus cos x plus c. So that iterative process is really important. You could have said at the start here that this is 1, this is 2, and sub 2 into 1, and that allows for a little bit extra order there. Knowing that a is equal to and a is that original integral suggests that this is our final answer, this is our final integral. Alright, so our last one we're going to look at is a definite integral. So we're looking at the definite integral of ln x between 2 and 1. Now, the trick here again is to realize that we can treat this as 1 times ln x dx between 2 and 1. So I'm going to consider the integral of 1 times ln x dx in order to find the indefinite integral to put this back into the problem. Okay, so if we let u be the log, because we've got a log in a polynomial, so ln x dv dx is equal to 1, then derivative of ln x is 1 on x, and the integral of dv dx, which is 1, integral of 1 is x. So the integral of ln x dx is equal to uv, which is x ln x, subtract the integral of v du dx, which is 1 on x times x dx. So that means we're looking at x ln x, subtract the integral of 1 with respect to x, which is x ln x take x plus c. So now if I go back to considering the integral between 2 and 1 of ln x dx, it will be x ln x take x between 2 and 1. That means it will be 2 ln 2 subtract 2, subtract 1 ln 1 take 1. So we've got 2 ln 2 take 2, take ln 1 is 0, so we're taking away 0 plus 1. So we've got 2 ln 2 take 1 units squared. And there we have it. There is our integral of ln x between 2 and 1 as a definite integral, and a collection of integral by parts problems allowing for a range of complexities. Okay, thank you for listening to the lesson.